Yeah, that's all good. Some of them want independent.
I feel good. He's like, do anything to divide. Like, what was up to divide?
All right, good morning, everyone. We'll get started. So welcome to Medical 3D Printing. My name is Claude, this is Andrew, and this is Ricardo. So we'll just quickly introduce ourselves. So you might have seen this before in the intro programming course, but I studied medicine at Monash, economics at London, and then became a doctor for a little bit at the Austin. So did an internship year, wanted greater impact, so decided to study engineering at Stanford University on a Fulbright scholarship, where I was part of the product realization lab, which is the mechatronics lab at Stanford. Some cool alumni have come out of that, including Tesla's initial CEO before Elon Musk. And SPDL, which is SPDL is the mechatronics lab, and PRL is the 3D printing lab. So that's sort of the product design lab, product realization lab. And then I also studied biodesign at Stanford, which is a medical technology entrepreneurship course, which was fantastic. And then I decided to join the startup life and did a neurotech startup in the Bay Area. That's actually my device there. And so I just put that there because medical devices are a huge sort of burgeoning field. And so hopefully this is a sort of entry for you into the medical device field. And then I came back and joined MNHS faculty as well as the Faculty of Engineering just recently, just to sort of teach and give back to in the medtech space. Now this is actually me during the SPDL course. So we got to build like a little robot that could track another robot and then follow it around, which is really fun. So sort of like a relay race of robots. That took us, I think, like 2 weeks straight, about 16-hour days. But we eventually got it done. Now, along the way, I got to work at some cool places as well, such as the World Health Organization. So that was during my sort of public health phase, where I was like, so I want to do public health. Then decided to work, also did an internship at IBM as well, the University of Oxford, in surgical and medical AI, respectively. All right, Andrew, would you like to introduce yourself?
Yeah, so I'm Andrew. So I'm currently a third year at Warragul. So I decided to go rural this year. I'm originally from Queensland. And just a little bit about myself in terms of 3D printing and 3D design. So when I was younger, I built my own 3D printer from like just a box of parts, like a pre-built box, I guess, that I bought from a school for like $20. And yeah, I've been modeling and 3D printing for about 6 years now. And over the summer, I did a program with Hermione, which is the Monash Young Medical MedTech Innovators. And we did a little project there helping, working with pediatric urologists at MMC and designing an ultrasound device to try and read their bladder volume and diagnose different issues. And just below there is a little project I did for school, which was like trying to make a flying car. I'm interested in all aspects of medtech and hoping to pass on some skills to you guys. So yeah, pretty interested and pretty excited.
Awesome. And Ricardo?
Yeah, hey everyone, I'm Ricardo. I'm just a medical student from Hong Kong. I'm a second-year medical student, like most of you. I only started chatting about 7 months ago, and these two guys took me under their wing to learn about all of this. And I learned most of it through YouTube and just some notes on that. And yeah, I hope I can teach you guys some stuff.
Awesome. All right, thanks so much. So, I founded the Monash Medical Technology Lab, which has sort of 3 goals. So the first is to contribute to key research questions for medical AI. So this is more sort of on the CS side. We work with a new type of model called the foundation model, which is sort of an umbrella term for, ChatGPT, large language models. We work with all sorts of stuff in that space. The second is we actually train the next generation of medical technology leaders. And this is you guys, right? Like this is the work that we do in terms of teaching medical students, engineering students, sort of cool stuff in medical technology. And then the third sort of avenue of work is we do empower doctors to become stronger innovators with that biodesign methodology, which is one of the world's sort of world-class and leading methodologies for medical entrepreneurship. And we do that by working with, so we've worked with the state government to create a course for doctors to learn biodesign, and we also run workshops with mine. So why medtech? So a lot of people ask me, why do you do medtech? Why did you sort of switch away from clinical practice? And I like to break that question down into sort of 2 minor questions, which is why do I like medtech and why is medtech important? So why do I like medtech? So firstly, building and inventing, and hopefully you actually see that in this course. potentially more so than the coding course, is actually really super fulfilling, right? Like being able to hold something in your hands that you designed yourself, that you created yourself, that you understood yourself is something really fulfilling. Secondly, what you build can have massive impact. Okay, so when you create something, you know, it can become an invention that actually ends up in millions of people's lives, ends up actually having massive impact on their treatment or diagnosis. And then thirdly, this is a field where creativity and curiosity is strongly rewarded. Okay, so people who actually go out of their way to learn a lot more, to actually be curious about what they're learning, are often strongly rewarded because you just know a lot more than other people. Now, why is medtech important? It is one of the few levers in society to improve medicine, the other two primarily being research and development and public health. And so medtech is sort of a really big lever when it comes to clinical practice. Everything you see in the hospital is actually related to medtech in some way. Every device you use has been carefully designed by someone, or sometimes poorly designed by someone. I'm going to talk about some design principles there. Secondly, society does need doctors to invent. Okay, so we need doctors to be heavily involved when we're inventing stuff. If you imagine we have a society where doctors aren't involved in invention, you end up with a lot of devices that aren't fit for purpose, cannot be used in clinical practice. And then the third is, this is my own sort of personal thing, but I believe that future generations do deserve better medicine than what we have now. And so we're also responsible for either research and development, so improving that aspect of things by actually inventing and building things. Now, what exactly is medtech? So there are three sort of primary disciplines when you're thinking about medtech, right? And so you can sort of structure your thinking in this way. The first is digital health and medical AI. And so we'll talk just briefly about that. The second is medical devices, and then the third is drugs and biotechnology. Okay, so most people end up specializing in one, two, or potentially all, but all is quite rare. I've actually seen very few people specialize in all, just because they are sort of three separate fields with almost three different areas of expertise that you need to learn separately. So personally, I specialize in both digital health and medical devices. Now, medical devices are obviously a very sort of exciting area that is coming up right now. So, and you're going to learn some of that stuff sort of in this course, which is how to build a medical device, how to be thinking about medical devices as well. So medical devices, as you can see here, so on the top right here is actually the old pacemaker that we used to use, but now we have this leadless pacemaker that has started to come up, which means that you just basically embed that, transcutaneous, through the vascular sort of canal to the heart. And then you put that in the heart, and that acts as a pacemaker. Okay, so it used to be that you actually have to have a giant thing sort of underneath the skin, right? And that would sort of lead to another lead to the heart in order to sort of control the heart rhythm. We then have here basically this glucose monitoring device. So this is starting to become quite popular for type 1 diabetics. It basically monitors glucose, and then it sort of releases glucose into the bloodstream as required. Okay, so sort of tracks that remotely, which is really cool. And then this device here is an MRI. Has anyone actually seen an MRI device before? Yes, no? Okay, so if you've ever seen one in a hospital, it's actually huge. It depends probably the size of this room, right? But MRI technology is starting to be quite miniaturized. So it's starting to see very low Tesla MRI machines, which can basically do the job of an MRI very quickly on the bedside, right? So you can basically bring an MRI device out to the bedside and actually complete some of these scans remotely, which is a sort of cool technology that's coming up. Now, from a digital health and medical AI perspective, I won't dive into this because we all just did an intro to programming course where we dived quite a lot into some of these aspects. So medical AI, as we all know, is starting to impact things like radiology. It's starting to potentially enter surgery, right, which is always sort of lagging behind medicine. And then things like ChatGPT, you know, there's always sort of like a news article about whether ChatGPT is starting to potentially replace doctors or be able to do some of the stuff that we do. Now, there's a sort of third strain, which is not my area of expertise, but is starting to become really cool, which is drugs and biotechnology. So how do you actually modify things or treat things or diagnose things at the molecular level? And so we have things like Ozempic. So when I was going through med school, and even a few years ago, obesity was considered an untreatable disease. But now we have an injection that is actually seeming to be capable of treating obesity quite well. We have things like, cancer vaccines, so vaccines that basically treat cancer, prime the immune system to actually attack the cancer that you have. We have genetic editing, so just last year there was a sickle cell disease therapy that was approved by the FDA in terms of actually modifying a single gene and removing a disease from people. And then there's sort of cool technologies that are coming up, such as in vitro gametogenesis, which is basically a technology where you can take a skin cell from anyone, turn it into a sperm or egg of your choice. So that is, for example, males can create eggs and females can create sperm, and then you use IVF to basically create a baby. Okay, and they've tested this in, I think, small and potentially large animals now, and multiple generations now, there seems to be no sort of ill effects on the animals, right? Which indicates that it could potentially work in humans as well. All right, so why medical devices? So there are a couple of reasons why it's important to sort of learn about medical devices. So firstly, the human body does exist in a physical space. Okay, so this is obviously very different to, for example, the digital space. So when you're working with code, devices are the only way, even with code, to read or write at a macro scale. Okay, I added macro scale there because biotechnology operates at the micro scale. Okay, so that's sort of how I think about biotechnology versus medical devices. One is at the macro scale, one is at the micro scale. And devices are one of the few ways that we can actually affect real physical change. Okay, so if you, for example, just write code, it's very difficult to affect real physical change unless you have a physical effector in the real world actually doing something. Okay, so medical devices sort of bridges software with the human body. Okay, now medical devices is sort of split into 4 key engineering disciplines. The first is mechanical engineering, so we're going to be spending a lot of time on mechanical engineering in this course in particular. The second is electrical engineering, so we'll talk a little bit more about what that actually implies, because the body does use electricity, and so therefore you can interface at an electrical level. The third is computer science, so computer science obviously fuels a lot of the software that we use in mechanical engineering, electrical engineering, and so CS just sort of pops its head up everywhere, right? And then the fourth is material science, because we're talking about real physical things, there are a lot of material science challenges that we'll go through. So mechanical engineering. So mechanical engineering is a huge subdiscipline of engineering, and you'll see mechanical engineers who don't necessarily work in medicine as well. They can, for example, work in cars or buildings or whatever you have, right? And so mechanical engineering, as it relates to medtech, has sort of a couple of key subfields. The first is product design. Okay, so there is now a sort of rush for product design and good product design in medicine, right? Because we've had sort of decades of really poorly designed devices that have led to patient deaths, patient infections, all sorts of stuff. And so product design, and for example, I've just put Tesla's car there, is thinking about how the product actually looks to the customer, how it could be made beautiful, right? And so this is something that has come to the fore, particularly after the rise of Apple, when people realized that they actually liked using nice devices that just work seamlessly. Okay, and so you might see it around. A couple of people have Macs, a couple of people don't, but that's sort of like that design philosophy. The second is robotics. So robotics is starting to get big, particularly in the manufacturing spaces, as well as the sort of industrial robotic places, right? And so it has sort of yet to come to surgery. There's a couple of devices that are very simple that have started in surgery, so called like the intuitive surgical Da Vinci machine. It's just a device that simply removes any tremor from surgeons' hands, allows sort of more access of freedom, right? Like degrees of freedom to actually operate on. But there is sort of an exciting subfield that probably in the next few decades is going to be sort of a huge explosion in robotic surgery. Now, third is biomechanics. So this is understanding the mechanics of muscles, bones, like that sort of stuff. Why is that important? Obviously there's things like space medicine where that heavily relies on subfields like biomechanics, so you need to understand the sort of different forces that are occurring on people's bodies, right? And so as you go into space, for example, the different forces do completely change. If you don't understand those underlying equations, it's very difficult to predict what exactly is going to happen to someone if they're in space, for example, for an extended period of time. Now, there's also fields like flow dynamics and thermal simulations, which is understanding how blood actually flows in the heart, how blood actually flows, for example, in the arteries, and how heat distribution actually works as well. And so those subfields are part of mechanical engineering. Now, electrical engineering. So electrical engineering, again, is another very vast field. As you can imagine, if you become an electrical engineer, you can really sort of do anything relating to electricity. How it relates to medicine is one, signal processing and imaging, right? So that is a sort of huge subfield of electrical engineering that's dedicated solely to sort of advances in imaging. And so some exciting work, for example, and that is, the creation of a very low Tesla MRI. That took a lot of work, probably like 10 or 20 years of research before that, right? Related to that as well is, can you, for example, create an MRI? So MRI imaging takes a long time. If you have a Saturn MRI, it takes about 40 to 60 minutes. Can you actually shorten that length, right? So there's a lot of active research going, can you actually do a 10-minute MRI instead and still get the same information out? Okay, so that's like an active sort of research problem that is happening right now. Then there's things like sort of implants and, what's that? Is that mine?
Ringing the phone.
Oh,
It's a scam call.
No way.
How did they get the Monash number?
Okay. So there's things like implants, so a lot of the body does operate on an electrical signal, and you can interface with that, right? So one of the sort of earliest examples of that, and that was through an Australian inventor, is the cochlear implant, right? The ability to actually connect with the cochlea and talk to it at an electrical interface and provide information about the sound that's happening around us. Now, there's all sorts of wearables because electronics are starting to get thinner, it's starting to get easier to use, they're flexible as well, right? And so can you, for example, interface with the body through a very sort of thin, wearable, flexible thing there? Now, this is a brain-computer interface that was invented by an Australian neurologist in a company called Synchron. They just raised, I think, like a 40 million Series B or something with a big VC in the Bay Area. But this is a stent that also acts as an electrode. Okay, so stent, hence stentrode, right? And you basically put it through the vascular to an area of the brain, and then it interfaces, it reads and writes with the neurons around that stent. Okay, so sort of a new technology that's coming up, and some people argue that this may be even better than Neuralink's products. Okay, so sort of the real future of brain-computer interfaces. And then things like exoskeletons, is that sort of being used in medicine? Not really, but it's being used in sort of industry in terms of just actually helping people with their day-to-day tasks that may require some physical labor. Now, material science, so we won't talk very much about material science, although you will hear about different materials you can use for 3D printing. But material science is sort of a very active field right now that has a lot of challenges, and a lot of our challenges in other fields really relies on whether material science can figure out some of their key questions. So for example, I have this sort of Neuralink thing there. One of the things with brain-computer interfaces is that if the electrode is too large, basically what happens is that the brain actually scars around the electrode. So after some time, it literally gliosis around the the electrode, right? And so therefore they found that if you can get an electrode that is sufficiently thin, so I don't remember, I think it's 1 micron or something, then the brain actually cannot detect that as a foreign presence and therefore doesn't scar around it. Okay, so that's a huge sort of material science effort that's happening now because they're seeing, you know, if you can create an electrode that's sufficiently thin that the brain does not scar around it, because every other brain-computer interface, if you shove it into the brain, after a few years, it's just going to scar and you have to take it out. Okay, so that's one of the key challenges right now Elon Musk has been having, because they actually put this in the first patient. I don't know if you saw some news on that. They put this in the first patient, and after 6 months, it just stopped working. And they had to take it out, right? And that is because it's a material science challenge. Now, there's also things like Implanon, which is basically a drug depot. How do you extend the life of a drug for a really long time, right? Can you, for example, use a depot for other drugs, you know, for example, for something like pain, where you have like a local anesthetic depot that just stays in a certain area, for example, post-surgery, and it reduces the pain and inflammation around that area for 6 months, rather than sort of like a few days, which is what we have now. Now, there's also obviously stuff related to biomaterials and, for example, hard stents and biocompatibility, sort of biocompatible materials, right? Can we create materials that have certain properties that we want? So, for example, the ability to sort of, maintain heart flow or be resistant to sort of the really quick, rapid blood pressure that you get for really extended periods of time, right? Because a lot of heart stents, they sort of fail after 20 years. And you get one that's like 40 years, 60 years, 100 years, right? So these are sort of key questions. And then I've also put here sort of a brain organoid, which is this new technology that's rising. So it's a brain organ that you actually grow in a cell, and it actually computes like a brain, right? And so there are some sort of key ethical questions there, right? If you develop brain sufficiently, is that just like as if I exist, but in a sort of petri dish instead, right? Because when do you know at what stage people actually have conscious thought, that sort of thing? So there's people are sort of pushing the limits of these brain organoids, but obviously at some point, you know, that brain starts to develop conscious thought, but it sort of exists sort of outside of the physical body, which is wild. Okay, now there's a sort of related field, which is mechatronics. And so I talked about that before. What on earth is mechatronics? It's a combination of electrical engineering, computer science, and mechanical engineering. So it's a combination of those three, and it's particularly useful for devices that require electricity. Okay, so a lot of medical devices require electricity at some point. We won't really be talking about this much in the sort of next 2 weeks, but it is good to be aware of that this exists. And so what mechatronics is is actually reliant on this thing called a state machine, which basically tells you the different states that something can operate in. And so a lot of our world actually operates based on mechatronics. And so this is a state machine for a microwave, which is that a microwave generally has three states. One is ready to cook, two is door open, and then three is cooking. Okay, and then based on what a user does, so for example, if you press a certain button, it switches it to a different state. Right, so for example, door open to ready to cook means that you just close the door, it detects that, and then it knows that in that state it can do these options. Okay, so just something to be aware of, something to think about. Now, this here is a device that's a vagal nerve stimulator that's transcutaneous, right? So it's a sort of non-invasive vagal nerve stimulator, which is really cool. That's recently been released. This is a new technology to treat essential tremor, which is when you sort of just have a tremor. It retrains the brain so that it sort of prevents that tremor pathway from happening. So you use it over time, and then that tremor disappears. And then this is, for example, a very beautiful ventilator. Okay, so this is sort of a new technology that's coming up now at a Stanford called One Breath. And again, you see how the product design is very nice, very different to sort of existing ventilators, which you may have seen in hospital and are sort of a nightmare to use at times under pressure. All right, so why product design? So product design, like I said before, is sort of the overarching umbrella term for 3D printing. So 3D printing slots within product design. Now, product design itself has a very rich design history. Okay, so we're talking about the ability to actually understand the user, empathize with their problem, okay, defining the problem, thinking of ideas, prototyping, and then testing. Okay, so it's a process that sounds really basic, which is you put the user first, but a lot of people haven't done, didn't do, has never sort of been in medical devices until recently. And so this is something that we want to make sure that you guys think about, particularly for your project in the second week as well, right? Are you solving something for an actual user? What are the things that you need to be thinking about? Now, good design matters, right? Like, so this sort of became true the day that Apple became successful, right? Where you have a device that works seamlessly and people start to think about, like how do you actually design a seamless user experience for the people you're trying to sell to? And so there's all sorts of things that are sort of hilarious in medicine / like dangerous. And so EMRs or electronic health records or electronic medical records were supposed to be sort of like a huge, like sort of influence in medicine, right? But people just ended up hating the software if you ever end up sort of using it in clinical practice. At the Austin, we joked that it just kept on breaking down every single week, right? Like it just break down, then you have to switch your paper. And you haven't written in so long because you've been trying to rely on these electronic health records, right? And so there's so many issues with electronic health records. I've seen some of the work by the digital health team, and it's just funny the sort of bugs that they get in terms of, if you click there, something intuitive, it could lead to sort of disaster for the patient down the line, right? And now this is sort of a funny thing where it's an adrenaline injector, right? But it got recalled because a lot of people were accidentally injecting their thumb. Instead, right, like the way that it was designed, it was unintuitive which way you should be holding the actual thing. And so a lot of people would hold it upside down, and instead of injecting it into the patient, it would go straight through their thumb, right? Which is not a great sort of thing to have. And so, yeah, so this is the sort of examples of poor design in medicine. And so good design does really matter. And if you ever decide to work in medical devices, you really have to be thinking about all the ways that your products can be misused, right? And there's sort of this saying in the medtech field that, when you're creating something, physicians will find a way to fuck it up somehow, right? Like they'll find a way, a very stupid way to misuse your product somehow. All right, now product realization. So we'll talk about some of these technologies later. But product realization has actually multiple sort of ways of manufacturing. And so we'll introduce you to some of those. On this side here, so product realization has sort of two key pillars. The first is a technology called milling, which is, and we'll show a device later, but basically a device that cuts out metal or any material you have in a certain pathway. Okay. And then the second is what's called lathing, which is it uses a rotating object to be able for you to carve out certain things. Okay. So we'll go through what this means, but this is sort of the pillars of product realization. And so creating a product, actually there's three main ways of doing so. And so we'll give you a little bit of a tour, and then we'll go back to 3D printing, which is part of this last one here. So the first way is, the first one that we'll cover is something called subtractive manufacturing, which is basically you have a product and then you want to subtract stuff out. Okay, so just imagine like a block of metal, and then you want to cut stuff out in order to get what remains. Does that make sense? So you're subtracting sort of material out. The second is you're adding material, so you start with nothing, you have like a completely blank canvas in front of you, and you're adding material to create something, okay? And then the third is you actually have pretty much what's called a cast, which is you have like a sort of like enclosed space, and then you fill it with a certain material, and then you sort of let that material go. Like you take away the sort of structure there, and then the material falls out. Does that make sense? So those correspond to subtractive manufacturing, additive manufacturing, and formative manufacturing, respectively. So let's talk about the first subtracting, which is what we called milling before. So if you ever see this device in the machine shop, it's called a milling device. And how it works is basically, say you have this block of metal, right? You can actually, you have this drill bit here, so which is generally attached to this component here. You put the block there, and then you turn the machine on, and it just becomes like a drill, right? And then you put the sort of, you connect the device, so your block of metal with this drill, and then you cut out something. Does that make sense? And so it's particularly useful for particularly, complex geographies where you need, for example, like a cylindrical hole, or you need like to cut a square or something like that. Does that make sense? So that's milling. The second is lathing, which is you have this giant device where you have this block that rotates like this. Okay, so you put something on that block, and then you use this cutter to basically cut out volumes of revolution. Does that make sense? So something where it's like essentially a volume of revolution, if you recall from mathematics. And so you can cut out sort of different sections here. And so certain products can be created with both milling devices and lathe sort of devices. But certain products are better oriented, for example, towards a mill or lathe. Okay, so this again is just a small piece, but it's something to be aware of because Monash actually does have these devices. So if, for example, you want to create something from metal using these devices, this is just a pathway that you can take. Now, sort of connected to lathing as well is what's called a boring device, which is instead of sort of cutting the outer edge, you're cutting the inner edge. And so this is how sort of cylindrical holes are often created using a lathe device. Now, these devices, these methods have also been sort of subjected to computation and automation, right? And so what you can actually do in some of these software is plan out a certain path that is pre-automated, right? So pre-planned, and then you completely automate the creation of these devices. And so, for example, this here is a CNC milling device, which basically cuts away. So you plan the path that the milling device actually operates on, and then cuts it automatically for you. Okay, so these are sort of new devices that are starting to come up. And this here is what's called a 5-axis CNC milling machine, which basically means that it can basically rotate through multiple axes to get a certain finish that you want. Okay, so these devices have become very powerful and almost standardized in the industry because it allows you to create stuff at scale very, very precisely. Now, related to that as well is what's called CNC lathing, which is you pre-plan stuff on a lathe device, and then you basically tell it exactly where to cut, how much to cut. And so this, for example, is a rook in a chess piece, right? And so you see how you can basically plan out to very sort of high precision exactly where to cut on a thing that's rotating. Okay. Now, related to that as well, and this is a technology that you might see around, particularly is accessible to people who are starting out in product design, is something called laser cutting, which is basically you use lasers to cut through, for example, a wooden piece or a metal sheet, right? And so this also is very useful just to create out two-dimensional type shapes, right? And so it's something that I believe also exists here as well. Now, related to that is water jet cutting. So this is, again, a more advanced technique that uses water jets to cut powerfully through sheet metal. And so water jet cuts are more expensive, but they do provide a much better finish as well. Now, electrical discharging is sort of the final subtractive technique. And this covers basically using this electrical cable and then using a spark from that electrical cable to powerfully cut through metal. Okay, and so this is sort of done underwater, and it's very powerful for cutting very large blocks of metal. Okay. All right, so back to sort of subtractive. So recall subtractive is when you start with a certain block of the metal, and then you cut away components to sort of leave something behind. And then next is additive. So this is what's called fused deposition modeling, or known as 3D printing. And this is sort of the main 3D printing technology that you'll be using. Essentially, you start with nothing, but then this here, and Andrew will go into more detail tomorrow, deposits a layer of plastic So it's sort of like an inkjet printer where it just prints layer upon layer. Okay, so that's called fused deposition modeling. Now we'll talk about this on Thursday, but there's another 3D printing technique that is particularly popular for medicine because it can use biocompatible resins called stereolithography. Now this is actually the original 3D printing method, but how it works is that you have a bath of resin here, and then this UV light that prints every single individual layer. It takes it out, it refills that resin bath, and then it puts it back in. The UV layer solidifies the resin, right? And then it pulls it out again, and it keeps on repeating. And so you basically print something upside down and sort of in reverse like that. Now, there are also other sort of 3D printing methods that are starting to pop up, which is selective laser sintering, for example. This is particularly useful for 3D printing metals. It basically turns a powder and then it compacts it using a technique called sintering. And so that allows you to 3D print metals. Okay, again, more expensive, but it does allow a much wider range or a different range to 3D printing in terms of the materials that you're using. So instead of plastic, you're more likely to be able to print metal powder. All right, and then the sort of final technique from an additive standpoint is material environment jetting, which is another advanced technique where it basically jets out a certain metal. So, and then it cures it using a special sort of binder, right? And so this is, again, a very quick, very rapid method for a certain certain range of material. And for example, you can see here the sort of frame of a door being made and sort of the structure of that door being made. Using this technique called material binder jetting. And again, it's an industrial grade one, so it's not one that you sort of have ready access to unless you're intending to invest like millions of dollars on. Now, I've also added this one here, which is called direct extrusion. So this is how a lot of food or some metal objects are made, which is you extrude out or you push out a certain object, and then you actually basically cut away that object and then use that structure for something. So this is just, for example, a GIF of pasta being made using direct extrusion, where they're pushing out a certain material in a certain angle, and then you just basically cut away that component. All right, so that's the additive manufacturing sort of field. Now, formative in manufacturing field, one of the main sort of techniques is a technique called injection molding, which is how we currently manufacture plastic at scale. And so how injection molding works is you have this huge device here, you put in plastic pellets through here, and then it pushes out the molten plastic into a certain mold, right? And then that mold gets pushed out, okay? So it just keeps on repeating that very, very rapidly. So these cycle times are probably on the order of seconds. It just pushes it in, pushes that piece out. And so you can very quickly manufacture almost millions of plastic pieces within sort of a few weeks or a few months, right? And so this is how, for example, things like Lego pieces or most of the plastic things that you see are currently created. Now, there's a sort of related technique called sand casting, which is a common technique to actually create metal components very quickly. And so you firstly have a mold, you tamp it down with sand, right? And then you pour in molten metal, and you might have seen that step before. So it's going to repeat again here. You pour in molten metal, and then it enters that mold, and then you take out the sort of sand, and then you have a nice piece waiting for you, okay? And so this is how, for example, a lot of car pieces are made, in terms of pieces that you need to manufacture at scale using metal, okay? All right, and now this is a sort of older technique called die forging, which is, if you recall, forging from Game of Thrones or something, where they're trying to actually forge a sword, right? They basically heat up a piece of metal, and then they try to shape it with a hammer. Right, we now have a newer technology called die forging, which is you again heat up a piece of metal, right? It turns really red, it turns really hot, and then you actually forge it using a certain sort of almost like anvil-like structure that has a shape within that anvil, right? And so it just basically creates, again, products at scale, and it's sort of a powerful technique for really sort of hot metals or really strong metals that need to be heated to a very high temperature. Now, this is another popular technique as well, and this is the primary technique for a lot of sheet metal stuff that you might use. So, for example, bowls, like aluminium bowls or sort of, cooking utensils, that sort of thing. But how this works is you have a sheet of metal that comes in, and then it gets stamped to a sort of pre-selected shape. Okay, and as you can see on the actual product on the right there, this is how quick it is. And so you can create aluminium bowls, for example, or helmets or whatever you have, sort of really quickly at scale. All right, now sort of related to all three of these techniques is what's called joining techniques. So how do you actually join different components together? And so if you, for example, you have two metals, you can use a technique called welding, which is you basically heat the two metals to a very high temperature and then it forms a bond using sort of melting of the metal. And then this is another technique that if you ever sort of study mechatronics, you will have to learn about, which is called soldering. And soldering essentially connects two metals together, two conductive metals together, using a conductive medium. And so therefore you can complete an electrical circuit. So before you solder, this sort of wire here and this component here are not electrically connected. But then once you add solder on, it is now electrically connected because they're all conductive material. Okay, and that's something that you can both do manually and also get someone to do at scale for you. So there's a very sort of quick soldering device that automatically does it. But when you first start off, you actually need to do this manually. And some people say that, you know, this is actually harder than surgery because it's even smaller than most surgeries. But yeah, again, something interesting to be aware of when you're dealing with joining. All right, now a sort of plug for the Monash Makerspace. So fortunately, we've managed to find access for all of you through the Monash Makerspace. And so this is something that is sort of a new initiative that we're starting, which is medical students can actually access some of the engineering faculties that exist. And so Monash Makerspace has sort of two main spaces, which we'll see, I think, one later tomorrow. But one is the 3D printing space where you actually get to work with, a lot of the sort of printers that exist. They have a whole range of printers that you can operate on. And then the second is, I don't know what the space is called, but it has a milling machine, a lathing machine, all sorts of other sort of devices where you can physically make something. But you do need to go through training for that, and some of that training costs some money as well. But it's just good to be aware that you can operate on these two spaces. Now, why 3D printing? And this is an important question. And so 3D printing is a great starting point for additive manufacturing in particular, right? So a lot of product realization courses first teach you milling and lathing as sort of subtractive manufacturing, so starting from that base. But 3D printing is starting to get very hot. So there's really cool sort of research advances in 3D printing, and 3D printing also works very well with medicine as well. And so we have, for example, a medical 3D printing lab here that is actually one of the top in the world. And so medical 3D printing is starting to become a very good thing. And 3D printing itself is great for prototyping. So at some point you will end up using 3D printing when you create a device just to answer key questions about your device, right? There's nothing like sort of having something in your hands and using it to answer sort of key design questions or key technical questions that you might have. It's also very accessible. It's very low cost. So for example, this is what's called the Creality 3D Ender, which is a very sort of entry-level 3D printing. I believe it's around $250, right? It's a very sort of cheap 3D printing system that you can build yourself, have at home. You can use that at any point in time. It's very low cost to start, and it's very intuitive as well because you're adding something rather than subtracting something, right? And there are a lot of sort of online resources now available, with whatever question you might have about 3D printing. Okay, so it's sort of something very easy to get off the ground for product realization. And it's also increasingly powerful. Okay, so 3D printing is getting, starting to get quite good in terms of resolution, in terms of the cool stuff that you can actually do with it. And so here's, for example, 3D printing for anatomy training, right? So it's just like teaching the different vessels that exist in the brain. There's starting to be glass 3D printing, which is you can actually print glass, right? Like clear glass. And there is a company in Fitzroy that actually does that for you, right? There's also things like generative AI getting involved in 3D printing. So how do you, for example, create a structure that has minimal weight, minimal material, but still provides a lot of strength? Okay. Now, 3D printing is also starting to enter fields like orthopedics, right? Like how do you actually print stuff that again fits someone's anatomy and actually uses as little material as possible, but provides as much tensile strength as possible. And then this is a sort of new field that's coming up, which is you can 3D print tissue now. And so can you, for example, create tissue that actually covers wounds or create tissue that does some other sort of aspect of medicine? All right, now the goals of this course are to, one, provide you a strong 3D printing foundation. Okay, so we're hoping to sort of provide you a lot of practice with CADing, a lot of practice with 3D printing, and we are going to provide a project at the end as well, where you actually work in teams to create something with us. The second is we're going to introduce some exciting medical 3D printing paradigms. So there's a lot of cool stuff that's happening with 3D printing in medicine, and so we'll talk about some of that as well. And then the third is that there is no prior 3D printing experience required. So some of you, I think, in the room have significant 3D printing experience, but some of you don't, and that's perfectly okay. We're going to start sort of from the beginning. Now, how are the days going to work? So day one is CAD. So today we're going to be working on a lot of CADing skills. So CAD stands for computer aided design, which is can you actually design a product in a software called Fusion 360? And we'll send that out very soon. And what you're going to be working on today is just orientating yourself with CAD, learning how to sketch properly, how to do things like extrusion and cutting, how to learn sort of more advanced techniques like revolving, sweeping, and lofting. And all that will become clear later today, what that means. On day two tomorrow, so this will be, Andrew will be teaching this, it will be 3D printing 1, and we'll go through the basics of 3D printing, how to set up a 3D printing device. You actually get an induction in the Monash makerspace, so they'll run you through how their 3D printers actually work. We're going to be talking about some basic material stuff, how to model for 3D printing, how to use what's called a slicer or slicer software, as well as how to troubleshoot 3D printing machines. So when you start dealing with hardware, getting in comparison to software, bugs do come up, but they don't give you an error, right? And so you have to figure out physically, based on looking at what you're seeing, what is actually happening and how to fix it. Day 3, so we're going to go back to CAD. So CAD is again a very key skill when it comes to 3D printing, and we'll go into some more advanced features like things like threads, rendering, molds, analysis that you can do in these software, as well as a lot more practice about CAD. Day 4 is going to be focused entirely on CAD exercises. So we're going to give you quite complex stuff that we need you to actually make, right? And we're going to help you sort of run through that as well. There's going to be a technical lecture that's going to cover useful tidbits, which is just almost like a miscellaneous collection of topics. So for example, like SLA printing, dimensioning and tolerancing, like sort of different topics that bring everything together. Then day 5, we're going to introduce you, so we're going to have a bit of a lecture on medical 3D printing and then introduce you to your project, where you actually work on for the rest of the next week. And so you'll be working in teams of 3 on this project. And so next week as well, we'll go through a number of technical lectures. So one on post-processing on Monday, the second on reality capture and algorithmic modeling on Tuesday, and then on either on Wednesday or Thursday, depending on timing, manufacturing at scale, the future of manufacturing. Okay, so what to think about, for example, if you want to manufacture millions of your projects rather than just one. Okay. And then on day 10, there's going to be a really sort of exciting show and tell, where you show and tell us, what you've actually created, run us through the process of what you made. And we've invited a couple of guests here. So the first is guest speaker, Associate Professor Jason Chuen, who is the Director of Vascular Surgery at Austin Health, as well as Director of a 3D Med printing lab at UniMel in Austin. So he's going to give a bit of a lecture on his research and what's sort of exciting in 3D printing right now. Michelle Leach, I believe, is going to come as well. So she's going to come and actually see some of your projects, which is going to be really exciting. And we might have a photographer and videographer in those days as well. All right, so some disclaimers. These sessions will be recorded. So we've had a number of faculty members ask us for these lectures. And so we're just going to be making sure we record them. The recordings may be used in other contexts. On the last day, there's going to be guest photography. If, for example, you don't want to be in the photography or the video, just please reach out to us and we're happy to sort of make accommodations. Now, in terms of the honor code, so we operate off what's called an honor code, which is please don't use pre-existing designs. So there are all sorts of resources you can use right now to download designs off the internet, but we do want you to make this by yourself so you can learn the process of actually doing it. If you're stuck on something, we're here to help. Okay, we don't have all the answers sometimes, but we are able to figure it out most of the time. And if you already know some of the material, please help us teach others. Okay, so some of you are quite experienced in 3D printing, but help us teach some of the stuff that you're learning. All right, teaching philosophy. So my teaching philosophy is that 3D printing or programming or engineering or whatever can be learned, practiced, and perfected by anyone. Okay, it is something that we've all been there in terms of just starting from absolute scratch, and we have a lot of key questions. And so if you have any questions, again, no dumb questions, just ask. If you have any questions, it's likely half the sort of room has it as well. In terms of educated expectations, my job is to create a welcoming environment for you to engage in this class, right? And my job is also to explain concepts clearly. We're not sort of perfect, and we'll, if there's something that's unclear, please just let us know, and then we're happy to sort of re-explain it as best we can. From a participants inspection sort of standpoint, we want you to bring a beginner's mindset. So actually ask a lot of questions, be curious, have an open mind, right? All questions are completely welcome. And we want you to actively and support the innovation community after you leave. It's a really small community in medicine. And so there's a lot of people who are still learning, and we want you to share that knowledge that you get from this course with the sort of rest of the community. All right, so this is the course website. So you might have already seen this in your emails, but if you haven't, please check it out. We're going to be posting all our lectures, all our recordings on this, even project stuff as well on this, and potentially even designs that we've made ourselves on this. And so this is sort of a central resource. And we also might update, we will update this website as we go along in terms of if, for example, we change a lecture, that sort of thing, right? Just based on how people are going. And then please tell us about yourself. So we did this as well in the intro to programming, but we do read every single response here. If you did already share something about yourself in the intro to programming course, please share something new and different, okay? But yeah, please sort of give us an idea of who you are, what you're here to learn, and something interesting about yourself.